By the power of Grayskull.
See, Dooley, He-Man has the power. I told
He-Man,
you, man.
He-Man thinks he has the power, but that's so old, Mr. Elliott. That's like 80s old. That's like, there's not enough power there. You want to see true power? Check
Yeah.
out Thor right now.
All right.
See, what did I tell you? Did you see how impressive Thor was? That was some serious power with one eye. Serious
I'll give
power.
you that. All right. Thor is impressive. The lightning, the thunder, very, very impressive.
You could almost say it's thunderstruck, right?
Thunderstruck. Exactly.
Thunderstruck.
It
Another
brings to mind 8 little AC/DC and AC/DC. Right? That's a type of current.
Yeah.
Oh
my
man,
goodness.
It's like it's all coming together.
Right. And didn't we see current in Ohm's law?
Oh my goodness. I can't believe you remembered that. All right. Okay. So let's talk power. Let's talk electrical power. All right. So we have, let me bring this up here. Do you remember when we did a lab on power?
Yeah, when we had all the kids run up their stairs at home and it was so much fun, right? Because they could calculate how much work they did and how much time they did it in.
Yeah. So power, if we to refresh people's memory, is just a rate that work is done or a rate that energy is used. So there's a lot of different ways that we can measure work or energy, and there's a lot of different types of energy. But how fast it's used or how fast it's done is how we measure power. So when we talk about this, we're looking at the rate. And remember, energy and work are both measured in joules. So that's joules per second. All right. So we've been talking current, which is how much charge is passing by per second. So that's a rate. We've been talking charge, which is just number of coulombs. And we've been talking voltage, which is how much work or energy a coulomb worth of charge can have. So we have Ohm's law, we have these other definitions. So here's our current, coulombs per second. Here's our voltage, joules per coulomb. So what we're going to do is take them and figure out a way to get rid of coulombs. And we want joules per second because that's what we're looking for right there. Well, if we multiply I and V together, the coulombs cancel out. All right. So we get P equals IV because power in joules per second is coulombs per second times joules per coulomb. And the coulombs cancel out. All right. So now we can figure out how much energy is used every second that an electrical appliance is on, how much work it should be able to accomplish. And remember, power is in watts. That's our unit that we use generally, but a watt is equal to 1 joule per second. So if you have a hair dryer that uses 1,500 watts of power, that means it uses 1,500 joules of electricity every second that it's on. What do you think, Dooley?
I really think that the key factor here is seeing that we get coulombs to cancel out, right? So ultimately, does the amount of charge passing through matter? Yes, it does, but it's all about the energy that those charges have and then how quickly we're able to get those charges to move. So does the current matter? Yes, the amount of charge that we have, but we see mathematically that the actual amount of coulombs, the actual amount of charge that passes, ends up canceling out for us. So
Right.
we can see higher currents and higher voltages leading to higher powers.
Yeah, because if we have high current and high voltage, we get a lot of power.
Mm-hmm.
If we have high voltage but low current, well, every amount of charge has a lot of energy, but there's not a lot going by. If we have high current and low voltage, well, we got a lot of charge going by, but not a lot of energy in each charge. So it's a balancing act.
Absolutely.
Do we have a water model like that?
Oh yeah, I think we do have. Of course,
Tell us about the water model.
Well, if we go to the next slide here, right? So this kind of becomes a combination of our waterfall and our river, right? Because now we need to take both the voltage and the current into consideration. So if you recall, for voltage, we looked at the waterfall model because that's all based on potential energy. Seeing electrical energy as a potential where it can do more work if it's taller versus being shorter, right? That gravitational potential that we can compare electrical potential to. So if we have a tall waterfall, we know we can do more work. And if we go to the river model, which is our current, well, if we have a tall, wide waterfall, that like wide waterfall, like Niagara Falls, for example, right? If we think about what Niagara Falls can do versus, if you go down to like Hastings and there's like a little 3-inch drop on a creek, there's a little bit difference between how much power you're going to get out of Niagara Falls versus that little creek down in Hastings, right? Big, wide river, lots of current can go through, can do more work than a small river. Tall waterfall can do more work than a shorter one. So if we really compare it, if you have physically more particles in the big river and they're higher, you have a lot of particles with a lot of energy. You're going to be able to do a lot more work that way.
Yeah. So if we can, like it says, if we can raise it up from a higher distance, that's like increasing voltage. So if we have a higher voltage circuit, it can do more work based on the drop in potential. But we also need current to go through. If no current is going through, there's not going to be any work done. So that's why we need a circuit. Mm-hmm. If it doesn't have a path that it goes, that's why your light bulbs are not turned on when your switch is off, because it opens up the circuit.
Yep. Right? Remember that continuous loop, everybody, right? We have to make sure that those charges have that full loop. Once that loop breaks, you're not going to do any work anyways.
Right. So talking about this, I cannot resist doing a couple of little examples. So a typical house has your plug-in has 120 volts. Now it's AC current, but it's 120 volts. So 120 joules per coulomb worth of potential. And most circuits in the house are 15 amps. So 15 coulombs per second are able to pass through. Now, that's different in different rooms in your house. The rooms that take a lot of electrical energy, which are what, Dooley?
And that's going to be your kitchen. That's going to be a primary one. Your bathrooms are going to take a little bit more as well. You need to think, where are the high energy materials in your house? And that's going to be your refrigerator. That's going to be your stove, your microwave. And in the bathroom, that's going to be, you're looking at, you have fans in there. You're going to plug in, hair dryers and straightening irons, right? Things, more your beauty and cosmetic items that require a plug-in are going to require more energy in order to do anything. But just like a standard bedroom, 120 volts is going to be just fine. And you're going to be able to run that on 15 amps.
Yeah. Generally what they do is put in higher amperage circuits in places where there's going to be a lot of heating elements or cooling elements. So stoves, fridges, air conditioners, clothes dryers, hair dryers, anything like that. All right. So a typical circuit in your bedroom is going to be 15 amps, 120 volts. So this is our voltage. This is our current. So P equals IV. We can just multiply those two together, and we find that can provide 1,800 watts worth of power. If you have an 1,800 watt hair dryer, and run it full blast, that's going to use up as much current as can be provided in that particular circuit. If you try to plug something else in, a couple things can happen. Either the hair dryer diminishes the amount of power, so it either doesn't blow as hard or get as hot, and the other object doesn't work to its full potential, or it'll draw so much current that the circuit will shut down in your house, and you'll have to go downstairs to the fuse to the electrical box and turn it back on. All right.
And that's why they're called breakers. And that's why they're called breakers. So if you find the electrical box in your house, that's going to control all of the circuits that exist. And when you pop the breaker, that means that it has physically turned itself off, because it's a fail safe for everything behind it. If too much current starts trying to flow through that breaker, it switches off and then saves everything from overloading and either breaking the devices or causing electrical fires that could occur. Now, what Mr. Elliott was talking about with that a heating element potentially not being on full blast anymore. If you plug in a vacuum cleaner and you turn it on, a lot of times in that same room or on the same circuit specifically, you're going to notice the lights diminish when you turn it on. And when you turn it off, you're going to notice the lights brighten back up again. It's because when you're running that vacuum cleaner, it is now drawing current from that same circuit, which means there's less current for the other items that are on that same circuit.
Yeah, it kind of depends on the sensitivity of the items that you're using. A light bulb will brighten or dim generally based on a more or less current, but some things can't deal with a change in current, so they'll just shut off or not work. All right. So if we have 1,800 watts worth of power, if we take 60 watt light bulbs, which is a typical light bulb of incandescent style, nowadays with LED bulbs, they're more like 10 watts. So you can get more LED bulbs. So that's why Christmas lights with LEDs, you can have that many more lights. But a 60 watt light bulb, well, we just divide the 1,800 by 60, and we can find that we could light up 30 different light bulbs if that's the only thing on the circuit, and they would be at their highest intensity. If we put a 31st in there, then all the bulbs would dim a little bit. All right. So you don't want to be that dim bulb. You want to figure this stuff out.
You want to be the bright bulb. That's
the bright bulb. Yep. Everything in that uses electricity has a amount that it uses. And Mr. Dooley, you want to talk about these?
Yeah. So on any electrical device, and you can find this on your iPad charging block. So if you actually take the block and look at it, you're going to see these ratings on it. If you pull the refrigerator out from the wall, you're going to see these. So if you look at the bottom right-hand picture there, it says a listed household refrigerator. That's a pretty common manufacturing sticker that they're going to place on electronic devices or devices that are going to require electricity. And what these are going to show you is what the max values are that they are going to draw in terms of power and in terms of current. It's also going to show what type of current is going to work best. So the KitchenAid in the top left there that says household use only, that is a mixer. That's going to be like a wall mixer that you would use, or a stand mixer that you're going to use to do like cookie batter or something like that in. That is only going to use 120 volts of AC current. So what is coming right out of the wall, it's not going to convert that at all. If you try to use less voltage than that, it's not going to operate. If you try to use more voltage than that, it's not going to operate very well there. Unlike, if you take, again, the block that you have for your iPad, that's actually going to convert the AC current in the wall to DC current to be able to charge the battery. And your battery actually requires less than that 120 volts. So we're going to see a step down in terms of the voltage that's actually going to be sent into the iPad. But these are very, very common. You can find these on any electrical devices. They're going to tell you frequencies of alternating current. They're going to tell you how much current it's going to draw when it's running at its highest capacity. So then if you start plugging other devices into that circuit, we're going to see the amount of current that it draws start to step down, which doesn't make it less efficient. It just makes it not quite as good at its job. It's not going to be able to operate at peak capacity, which you may not want all the time, depending on what that device is.
Yeah, so they always rate it by its maximum need. So, and they'll tell you 2 of the 3 quantities. They'll tell you the wattage and the voltage, or they'll tell you the voltage and the current, or they'll tell you the wattage and the current. So I circled up here on the upper left-hand one, that mixer. It said 120 volts, but it also says 0.6 amps. So we could figure out how much power that mixer actually uses. We could also figure out, okay, if I have a 15 amp circuit and I have this many amps already used, can it use this mixer? Now, I don't do that personally. I just plug it in and see if it works. And most of us do, but you could if you wanted to.
Right? Yeah, that would require you to go down to your breaker to figure out which circuit it's on and how much total current is going to be delivered to that circuit. So there's a lot of extra stuff that needs to happen there.
Right.
Not only can you find power here, you could also find how much resistance that mixer is going to provide in a circuit as well, because we know the amperage and the voltage. We could find how much resistance that mixer is going to have. And in the bottom left one, right, we see voltage and a wattage rating. So the 120 volts with a max power rating of 475 watts. From there, we can figure out how much current is needed to get to that max wattage. And then from there, go to resistance as well. So a lot of times we see this connection between Ohm's law and electrical power to help us figure out the entirety of the circuit or the device that we're working with.
So hopefully now you guys have the power to get done with the questions that we have to follow this lesson.
The resistance to these questions is pretty futile, folks, right? Do not resist, just do them. Be bright as you do so as well.
Shine.
It's what you should currently be doing.
It's been a pleasure.
It's always fun. Always fun. Thanks, folks.
Good luck, guys. See ya.
Bye.
You are beaten. It is useless to resist. Don't let yourself be destroyed as Obi-Wan did.